Let's return to the acceleration vector for an object moving on a circular path. We arrived at this expression by starting with the position vector, taking the time derivative of our position vector twice, and paying careful attention to the rotation of the r hat and t hat unit vectors as we move around the circle. So that got us here, and we conclude that the acceleration in general for an object moving on a circular path could have two components to it, a tangential component and a radial component. And so we would get the magnitude of the acceleration by using Pythagorean theorem on those two components here. So what are the two components? We've already discussed the tangential component, AT. This is our sort of linear acceleration in the direction tangent to the circular path. So our linear acceleration around our circular arcs, and it's equal to r times alpha, the angular acceleration, and it is identical to the instantaneous rate of change of our speed, v, our linear speed. So we recognize that the tangential component of the acceleration, that is the thing that changes the magnitude of your velocity vector. This is the part of acceleration that speeds you up or slows you down. The radial component in orange, on the other hand, the radial or centripetal component, centripetal meaning center seeking. We see it's center seeking because it's in the negative radial direction, meaning in towards the center of the circle. So center seeking, negative radial direction. The centripetal component equal to minus omega squared r, or equivalently the opposite of v squared over r. This is the form in which it's most familiar to us, negative v squared over r. This component of the acceleration has a different job from the tangential component. The tangential component speeds you up or slows you down. It changes the magnitude of your velocity. But velocity is a vector, and acceleration represents the change in our velocity vector. And a vector can change by changing its magnitude or by changing its direction. So the radial component of the acceleration, the centripetal acceleration, this is the part of the acceleration that changes the direction of the velocity vector. This is what keeps your object on your circular path. It's this radial component right here, this part, that takes your velocity vector and turns it by pulling always in towards the center. Pull in towards the center, and I turn that velocity vector. Okay, so in a way, these two components of your acceleration control what happens to your velocity. The tangential component, this is like your accelerator or your brake to speed you up and slow you down. The radial component, the centripetal acceleration, this is like your steering wheel to steer you, to change the direction of the velocity. Okay, let's move on to a quick discussion of uniform circular motion. So if you are moving with a constant speed and constant angular velocity and a therefore constant radial acceleration, centripetal acceleration, that would indicate that your tangential acceleration is 0 and your angular acceleration is 0. Note again how those two are related. So if these are 0, then v is a constant, omega is a constant, and if v and omega are constants, then the radial acceleration is a constant. That's what we call uniform circular motion. So just moving around the circle at a constant speed. In that case, we can represent your speed as the distance traveled over the time it takes. So it travels one circumference, 2 pi r, in an amount of time that we'll call the period. Give a capital T for period there. The number of seconds it takes to complete one cycle. So we measure period, its amount of time, as suggested by the use of the letter T. So it's the number of seconds per cycle. And I've got pink here to indicate quantities related to the amount of time it takes to complete full cycles if we're in uniform circular motion, or UCM for short. So period is the number of seconds. It's a time to complete one cycle. And your frequency we define as the reciprocal of the period. So if period is seconds per cycle, then your frequency, the reciprocal of that, is the number of cycles per second, or the number of revolutions per second. Sometimes we express that in revolutions per minute, RPMs. So all of these are units for frequency. And a common shorthand for that is hertz. 1 hertz represents 1 revolution per second. So hertz is our SI unit for frequency. It's one revolution per second. That's 1 hertz. Okay, so based on those definitions here, if the period is the reciprocal of the frequency, then this equation could be rewritten as 2 pi r times the frequency f, 2 pi r times the frequency f. But if I package it this way, and note that v equals omega r, the linear speed equals our angular speed times r, well then by comparing these two equations, we recognize that 2 pi times the frequency, that is equivalent to the angular speed omega. So our omega is also sometimes called the angular frequency. F the frequency, omega, which we have called our, let's see, it's had many names. Omega we have called the angular speed, the angular velocity, the rotation rate. Here's yet another name for it, the angular frequency. So 2 pi times the frequency, or 2 pi over the period. And omega, we recall, is measured in radians per second, or degrees per second, to distinguish that from frequency, which is revolutions per second, or the number of cycles per second. So frequency versus angular frequency. Angular frequency is angle over time. Frequency is number of revolutions, or cycles over time. Okay, time for kind of an overall summary here of our linear and angular variables. So I've got a column here for our linear variables, column for the angular variables, and the connection in between. So linear variables, that would be s, your arc length, v, your linear speed, and at, your tangential acceleration, meters per second, and meters per second squared. And we've got these derivative relationships to connect them. We can transition from the linear set of variables over to our angular set of variables, in which we use these Greek letters theta, omega, and alpha, through these connections. This is our fundamental relationship right there. S equals r theta. Take derivatives of that, and we get v equals r omega, and at equals r alpha. That's the connection from the linear side to the angular side. And over here on the angular side, angular position theta corresponds to our arc length s. Angular velocity omega corresponds in this way to our linear speed v. And we see alpha then corresponds to our tangential acceleration at. Radians per second, and radians per second squared are our units, and we see these derivative definitions. If you are moving in this other special way with a constant tangential acceleration, a constant non-zero tangential acceleration, then you would also have a constant angular acceleration based on this equation here. So if you have constant angular acceleration, we have a set of equations to describe that. Let's distinguish this from uniform circular motion, in which these are both zero. That was UCM over here. If these are non-zero but constant, then we get these two sets of equations. Our familiar constant acceleration equations for linear motion, we can apply these to motion around a circular path if we recognize that our delta x or delta y that would normally appear here can be replaced by delta s, your linear distance along a circular arc, delta s, and then v here would be your linear speed, and at your tangential acceleration. So all these equations can be applied. And equivalently, on this side, in our angular set of variables, we see that we get a very similar set of equations. In fact, we can take these equations and multiply both sides of each equation by r. In this case, you'd multiply both sides of the equation by r squared. And by applying these connections here, we could transform these equations directly into these equations. So these are your constant angular acceleration equations here. And the only major quantity that doesn't fit into this kind of summarizing picture of our linear and angular variables, the only thing that doesn't really fit into that picture is our radial acceleration, the centripetal acceleration. So that's why I've saved this color orange for it, because it's kind of special. Negative omega squared r, or the opposite of v squared over r. We recall that the job of this is to change the direction of your velocity, versus the tangential acceleration that appears here and here and here. That changes the magnitude of your velocity. That's what speeds you up or slows you down.